For the isotopic abundance and average mass activity, we are working with averaging, primarily weighted averages, and that's in an effort to understand what atomic masses and molar masses are all about. We're also looking at mass spectroscopy to understand where the abundances of the various isotopes of an element and their masses come from. So averaging, in the beginning here, we have boron, which we are told, of course, has 5 protons. Remember, all atoms of boron would have to have 5 protons because boron has an atomic number of 5. We see that on the periodic table. It comes as 2 isotopes, boron 10 and boron 11. So the difference between those two is 1 more neutron in boron 11. The mass number of boron 10 is 10. That's 5 protons plus 5 neutrons. The mass number of boron 11 is 11, and that is 5 protons plus 6 neutrons. We're told that the mass of each isotope is for boron 10, 10.013 U, and for boron 11, 11.010 U. We're also told that the abundances, which is from mass spectroscopy, are for boron 10, 19.9%, and boron 11, 80.1%. So we can approximate that with two isotopes for boron 10 versus 8 isotopes for boron 11. A simple average would be to just add the two mass, a simple mass average for boron. The two isotopes together would be 10.013 plus 10.013 plus 11.010 plus 11.010, that 8 times, divided by the total number 10, which would give this 10.811 U. The weighted average would be calculated approximately to be 2 over 10 times 10.013 U plus 8 over 10 times 11.010 U, equaling 10.811 U. Or using our more accurate abundances, the weighted average, the one which would correspond to what's on the periodic table for boron, would be 0.199. That's the abundance divided by 100 times the mass of that isotope, 10.013 U, plus 0.801 times 11.010 U, which would be 10.81. So that would be what we would see on the periodic table for boron, which is basically that. Mass spectroscopy. So that is an instrument that uses an electron beam, it uses a magnetic field, and it allows us to determine if we have a sample that's composed of an element of several isotopes. It allows us to determine the abundance of each of the different isotope plus their mass. So let's say that we're working with neon. Neon turns out to have 3 naturally occurring isotopes, neon 20, neon 21, and neon 22. Of course, being neon, they all have, with neon's atomic number of 10 neutrons, so we can from that, or 10 protons, so we can from their mass number figure out how many neutrons each isotope has. So the mass spectrometer we see in this figure 2, the schematic diagram, we have a place where we enter the sample, that would be the sample chamber. What it first encounters is an electron beam. So that's electrons being shot at the neon sample. What they act like is kind of like bullets hitting a target. They cause parts of the neon atom to go away. Electrons are what are shot away. So these high energy electrons hits the neon atom and causes electrons in it to be removed. So now we have a bunch of neon cations, and this device is set up so any cation with a charge greater than +1 ends up being collected on in a vacuum. So what we have in the ion beam is neon, the various isotopes, 20, 21, and 22, with a +1 charge. Now, they are charged and they are sent through an electric field, which accelerates them. So we have accelerating ions. Well, it turns out when they encounter a magnetic field, their pathway is bent. It is bent most for the lightest and bent the least for the heaviest. So the neon 20 would be bent the most, neon 21 in between, neon 22 the least. And where they hit the detector has to do with their mass. So how many times, for example, neon 20 hits the detector is a measure of its abundance. How many times neon 21 hits gives its abundance, neon 22 its abundance. And what we end up with is a graph that looks like figure 3A, the mass spectrum of neon. So the y-axis is you might say the number of hits. The x-axis is the mass. So from the x-axis, we could get the mass of each isotope. From the height of what's on the y-axis, we can get the abundance. We see that neon 20, the lightest, has the greatest abundance. Neon 21, there's a very tiny little peak for that. It's the least abundant. And neon 22 is then an in-between abundance. This same information was taken for magnesium, which turns out to also exist as 3 isotopes, magnesium 24, magnesium 25, and magnesium 26. So from the x-axis, where the peaks are, we see their masses, 24, 25, and 26 use. And from the heights, which we would measure, for example, just with a ruler, we get for the magnesium 24, its height to be 54.8 millimeters. The magnesium 25, its height is 7.2 millimeters. And for the magnesium 26, its height is 7.8 millimeters. So in this case, we see magnesium 24 is the primary isotope, the most abundant one, with magnesium 25 and 26 almost equal in abundances. From that, we can determine the abundance of each isotope. So we take the height of each one. Recall for the 24, it was 54.8 millimeters divided by the total. Remember that percent is always part over whole. So 54.8 divided by 54.8 plus 7.2 plus 7.8 times 100, since we're doing percents, we get 78.5%. For magnesium 25, its height, 7.2 divided by the height of all 3 times 100, 10 percent. We're down to 2 sig figs because 7.2 has only 2 sig figs in it. And then for the magnesium 26, its height, 7.8 divided by the total height times 100, 11. Again, 2 sig figs because 7.8 has only 2 sig figs. So that would be, from this information, how we would get the abundances. It turns out from a more careful analysis, we have the abundance of magnesium 24 to be 78.99%, 25 to be 10.0%, and 26 to be 11.01%. So very close to the numbers we calculated here. All right, now that's the intro, the lab write-up. The pre-activity, as usual, is not due. You're welcome to do it, but you need not. You do not submit it, but you will do the report and submit that. So put your name on it, ignore lab section. Part A is simple versus weighted averages. So we are working with thallium, and we have 10 thallium atoms, and we're told, although we could figure it out from the periodic table, that the atomic number Z is 81. That means there's 81 protons. And we have thallium 203 and thallium 205. And we're told what the abundances are, 29.5% for thallium 203 and 70.5% for thallium 205, which could be approximated with 30% thallium 203 and 70% thallium 205, or 3 thallium atoms for 203 versus 7 thallium atoms for 205. So first off, we're told to complete the table. So number of protons for each, number of neutrons. So mass number is, remember, number of protons plus number of neutrons. The number of electrons in the neutral atom, well, in an atom, by definition, it's neutral, so that means equal protons as electrons. We're told what the precise masses are. For thallium 203, it is 202.973 U's, and for thallium 205, it's 204.974 U's. Okay, so first off, we're calculating the simple average. And use the precise mass for that, so the simple average mass for 3 thalliums 203 and 7 thalliums 205. Next, we're calculating the weighted average. Now we're using the proper abundances, the 29.5% for the 203 and the 70.5% for the 205, and of course we're using the precise masses. The weighted average should be fairly close to the simple average, but a little more precise because we're using the more precise abundances. Are these values close to those given on the periodic table? They definitely should be. So the simple average of 2 isotope masses, so that would be just adding together the mass of the one isotope plus the mass of the other isotope divided by 2. Well, that's far from what we see on the periodic table, because this total simple average of just 2 isotopes assumes an equal abundance of the 2 isotopes, and we're told it's not equal. One is 29.5% abundant, the other 70.5% abundant. So that's what that problem 5 is all about. And since I've answered it for you, you need not answer it. Okay, part B, the mass spectra. We're working with bromine and chlorine. So if we ran bromine in a mass spectrometer, that would be our mass spectrum, the one on the left. If we ran chlorine, that would be its mass spectrum, the one on the right. So of course you know abundance is the y-axis, mass is the x-axis. And we're told to, first off, get out a ruler. So get a precise ruler in millimeters, measure the heights of all 4 of those signals. And we're told the precise mass of those signals. So the most left one in bromine, its mass is 78.9183, and you measure its height. And do the same for the second one, whose mass we're given 80.9163, and then do the same with the chlorine. So we have the precise masses given, you measure the heights. And then from those heights, with the percent, like we did above with magnesium, determine the calculated abundances of the isotopes of bromine and the isotopes of chlorine. Notice that the heights of the bromine isotopes are pretty equal. So hint, hint, you would expect the abundances for those isotopes of bromine to be around 50%. I see one's a little higher, so its value will be a little greater than 50, the other a little less. Chlorines, well, there's a definite difference between them. So we expect that to be reflected in the percent abundances. Okay, and then you're figuring out the weighted average mass. You're using the precise masses. We're using the calculated percent abundances, and you're calculating the weighted average mass of bromine, the weighted average mass of chlorine. And those should be very close to what you find on the periodic table. So the next problem is having us work with the mass spectrum of chloromethane, CH3Cl. So we learned above that chlorine comes as two isotopes, chlorine 35 and chlorine 37. We calculated their percent abundances above. Now, what we need to focus on is the parent molecule, this chloromethane, CH3Cl. So we have what are called form A of it and form B of it. Form A of it is the CH3Cl, where the chlorine has the mass of 35 U's. And the form B is CH3Cl, but our isotope is now chlorine 37. So its mass is going to be a little greater. So determine what the mass of form A is and what the mass of form B is, taking into account that each one has 3 hydrogens, each with a mass of 1 U, and each has 1 carbon with a mass of 12 U. So figure out what the mass of form A is, what the mass of form B is. Of course, form B will be 2 U's greater due to chlorine 37 versus chlorine 35. And then determine where those signals are on the mass spectrum. And then you measure. So in this table, problem 3, you're putting the masses you calculated for form A and form B in. You're locating those signals on the mass spectrum just based on their masses. You can ignore all the other signals. You're measuring the height of those 2 signals. And then from the heights, you are kind of like you did in the problem above with chlorine and bromine, you're determining the calculated abundance of just taking into account the height data. And then for problem number 4, you are answering whether those calculated percent abundances are close to those you calculated above for chlorine. In the part, let's go back to it, this part right here, this problem here. That is, do your calculated percent abundance from the analysis of chlorine MS in this part B, do they match your calculated abundances that you got in part C? Questions? Okay, so the first one has us work with an imaginary element Q, which comes as 2 isotopes, 127, abundance 11%, and 128, abundance 89%. So it's mostly the isotope Q128. So think about what the mass of that would be, the weighted average mass, you could call it the atomic mass, the molar mass. Think about what that would be given those 2 masses, 127 and 128, and those 2 abundances, 11 versus 89%. And that should allow you to answer question 1. Question 2 has you calculate the weighted average for gallium, given its 2 isotopes, gallium-69 with that mass of 68.93 U with the abundance of 60.1%, and gallium-71 with a percent of, oh no, I take it back. So what we're after in problem number 2 is using the atomic mass for gallium that we find on the periodic table. So look that up, what it is for gallium, that weighted average, the atomic mass. And we're told in this problem that gallium has two isotopes, gallium-69 and gallium-71. We're also told what the masses of those two isotopes. No, we're told what the mass of gallium-69 is. We're told what the abundances are of the two isotopes. So set up your equation to determine the the usual atomic mass equation. Put in what you know. You know the atomic mass of gallium. You know the mass of gallium-69. You know the abundance of gallium-69. You know the abundance of gallium-71. So your only unknown is the mass of gallium-79. So 71. So solve for that. Our next problem is we're told the atomic mass of gallium is 69.72 U's. So that would be the value actually that you would have used in problem 2. That's what you would see on the periodic table. We're told it exists as two isotopes. We know that, gallium-71 and gallium-69. And we are given a huge number of gallium atoms, that 1, 7, 0, 0, 0 with all those zeros. How many of them will weigh 69.72? This problem is only a conceptual problem. It involves no math. You just have to think about what is weighted average, what is atomic mass. In this case, it's 69.72 versus the masses of each individual isotopes. It's kind of tricky, but ponder it, think about it so that you can get the answer. In the last problem, it's somewhat like problem number 2. We have two isotopes, X93, we are given its mass. We have X95, we're given its mass. And we're given the atomic mass, the weighted average mass, to be 93.55 U. Calculate the percent abundance of X93. That problem is somewhat like problem number 2, but in problem number 2, you had the abundance, you didn't have the mass of gallium-71. In problem number 4, you have the mass of each one. The percent abundance of each one, will realize that the abundance of X93 plus the abundance of X95 has to be 100. That problem is rather like a problem that is in your Chapter 3 lecture handout. It's the example working with europium. So if you have difficulty with problem 4, look in your lecture handout, Chapter 3, for the problem dealing with europium, which comes as the two isotopes 151 and 153. We're given their masses, and we're asked to calculate the abundance of one of those isotopes given the atomic mass of europium. Alrighty, so when you're done with all of these problems, and all the whole report, scan it, prepare it as a PDF file, and then submit it in Canvas.